Hey guys, my name is Tensor. Welcome back to the Golang blockchain tutorial series. This is video 9 in this tutorial series. Thus far, we've built a blockchain that has all the key features that we really need. Anonymous and secure randomly generated addresses, blockchain data storage, proof of work system, a way to store transactions, and all of these features are crucial, but they're not enough. And that's because we need a network. Blockchains by definition are distributed systems, which means they should be shared between peers. And currently our blockchain only works on a single computer. The blockchain network is decentralized, so this idea of having like a centralized server is also completely removed from this type of architecture. Each of the peers maintains their own type of server in a way. That means all the nodes are directly connected to each other, and if we had a server, then that means that we would have a centralized point of failure. Inside of the peer-to-peer network of a blockchain, there are 3 different main roles. There's the miner role. They're the ones who are running the proof of work algorithm over and over and over again to mine the blocks and run the actual network. Then we have full nodes. Full nodes take the validated blocks from the miners and verify the transactions, and they have an entire copy of the blockchain on their node. So these nodes also perform things like routing operations, and they help other nodes to discover one another. Finally, we have SPV, or Simplified Payment Verification nodes, and these are essentially just the wallet nodes. These are nodes that do not store a full copy of the blockchain. Instead, they use Merkle trees, and they feed off of a full node, and they use the full node's information to essentially send and receive transactions. Because SPV uses the Merkle tree, they can verify their own transactions as well without having to rely on the full node, even though they don't have a copy of the blockchain themselves. For our version of this peer-to-peer network, we're going to simplify things quite a bit because we don't have multiple computers and because we just want to run it off of one local machine. We're essentially going to make it so that each piece of the machine contains its own version of the blockchain. In this video, we're going to actually build the logic for the network, and in the next video, we're going to implement it into the blockchain. So here we want to make a network module. So we'll create a new folder called network and then a file inside of it called network.go. And then this will be package network, of course. We want to go ahead and define some constants at the top of this file. So we're going to define the protocol that we're going to use, which will be TCP. Then we'll define the version, and this will be 1 by default. And then we'll define what's called the command length, which will be 12. I'll explain more about what the version and the command length are as we go further through our code. We want to also create some variables, and I'm sort of cheating with these variables, and then I'm using them to create persistent state across our nodes. However, this isn't really a great way of doing things. You would usually want to have some kind of data storage or some kind of memory storage rather than just using variables like this. We've got a node address and a miner address. The node address will be unique for each of the instance of the node that we have open, and this will essentially just be the port that we have open. So if our main node is, say, 3000, and the node address for that node will be 3000, and the next node is, say, 3010, its node address will be 3010, and so on and so forth. The miner address will be the node address of the node that is acting as the miner for the network. Then we'll have an array of strings called known nodes, and by default I'll put in localhost 3000, which will be our quote-unquote main node. This array of strings will contain all of the strings for the localhost addresses that are connected to this network. We need some way of describing blocks as they're being sent from one client to the next, so we'll create this 2-dimensional slice of byte, and then we need a way of containing our blockchain transactions, so we can create a map which contains a string which will be the transaction ID, and then the actual value will be the transaction itself. Our blockchain is going to have various different messages that it can send back and forth between each of the nodes, so we want to create different structures which will allow us to essentially identify the types of data that we want to send back and forth. So we'll have an address structure, and this will be a list of the addresses which are connected to each of the nodes. So this will allow us to discover the other nodes that are connected to any of the other peers. Then we'll have a block structure, which will take the address that the block is being built from and then the block itself, and we'll be able to identify where the block is coming from. We want to be able to get the blocks from one node and send them to another, so we can create a structure called getBlocks, which will contain an address. And when we call a getBlocks command, it will just go and fetch the blockchain from one of the nodes and then copy it over to another node. Then we'll have a generic getData structure. This will have the address string. Then it will have a type for the data. This could be a transaction or a block. And then it will have the ID of the data. So this part of our application will deal with actually getting the active data from calling a block or a transaction and sending it from node to node. Let's also create an inventory struct. This will have an address and a type. It can contain transactions or blocks, and then we can put the transactions or blocks into a two-dimensional slice of bytes. We need a struct to represent a transaction, so we'll have the address and then the actual transaction, which will be a slice of bytes. And then finally, we need a structure to represent the version. And the version has a version integer, a best height integer, and then a address from string. Let's kind of walk through the way that we want this network module to work. In our implementation of this network, we'll have our central node, which will be the localhost 3000 node. This is a node that all other nodes will connect to, and this is the node that will send data between all of the other nodes. We'll have a miner node. This is the node that will store the transactions in the memory pool, and then when there's enough transactions, it will mine a new block. And then we'll have a wallet node, and this is a node that will be used to send coins between wallets. Though unlike an SPV node, it will have a full copy of the blockchain. Here's how the algorithm will sort of work for our network. So first we'll create the blockchain with our central node. Then we'll connect with a wallet node, which will then download the blockchain from the central node. Then a miner will connect and again download the blockchain from the central node. The wallet will then be able to create a transaction, and when they do that, the miner will then get that transaction and push it into their memory pool. When we have enough transactions, we'll then be able to mint a block using the miner, and then that block gets sent to the central node, and then the wallet node syncs and verifies that that node and the payments in the node were successful. Each of our nodes is going to communicate with one another using messages, or what are called RPCs, which stand for remote procedure calls. The most important of these remote procedure calls is this version structure. Now the idea of this version is essentially to make it so that we can sync the blockchains between each of our nodes. So when a server connects to one of our nodes, it will send its version of the blockchain, and then it will get a response from that node with its version of the blockchain. So we're essentially just checking the height of the blockchain, meaning the length of the actual chain. And we're saying, okay, well, my blockchain is, say, 4 blocks long. Yours is only 2 blocks long. You need to download the other 2 blocks and then add them to your blockchain. Then we'll increment the version based on how many blocks are in the chain, and we'll be able to sort of keep this version as a central piece of state to identify when a chain needs to be updated. We're going to be sending all of our commands to and from our nodes using bytes, so we'll create some helper functions, one called command to bytes and then the other one called bytes to command. And with the commands to bytes function, we'll take in a string and then we'll create a byte array that has a length of the command length which we added up top. So it'll always have a length of 12 bytes. And then we'll take our string and we'll split it into characters and we'll assign it to our bytes array and then pass it back. Then we can deserialize it in the same way where we just take each of the bytes and then we take them and we reconvert them back into a string. And we just need to make sure that the byte is not 0. So we just check to see if b does not equal 0, then we want to append it to the command. So if there are any spaces in the command, we can remove them. Before we go a little bit further, let's go on a bit of a tangent here. I'm going to bring in this library called def. Before we go any further, let's go on a bit of a tangent. So because we're using BadgerDB, we need a way of actually closing down our database if we hit Control-C. So I'm going to use a library called def, which will allow us to actually intercept that signal and then terminate the program by closing down the database and then actually quitting the application. Here's what that function's going to look like. So this is called closeDB. It takes in our blockchain. Then we use our death library to create a new death object, which will take in these signals. So syscall sigint, syscall sig termination, and then os interrupt. These two signals on the left are the two that will work for Linux and Mac operating systems, and then the one on the right is a signal that will work for a Windows operating system. Once we have our death object, we can then call waitForDeath with a function, and then we can execute a closure when the death occurs or when we actually terminate our application. So we'll defer OS exit 1, and then we'll defer runtime go exit so that we actually properly kill any go routines that are running before we exit the application. And then we'll call chain database close to close down the database gracefully before the application quits. Now let's create a encoding function. This will just take in a piece of data, and we want our data to be nondescript, so we'll pass in an interface, and then we'll take that data and convert it into a slice of bytes. Again, this is like all of the other serialized functions that we've created in this application thus far. We create the bytes buffer, then we use a gob encoder to encode the data, and then we pass back the bytes. We'll mainly be using this function so that we can send our commands to and from our application, along with the blocks and the transactions and all of our structs, really. Now let's actually start to set up the network part of our application. So we'll create a handle connection function, which will take in a net connection and then our blockchain. We can use IOUtil to read all from the connection, and that will give us back a request and potentially an error. We need to defer closing the connection, and then we need to handle the error. And then with the request, we can pull out the command like this, and then call our bytes to command to get the command, and then we can print out the command. And then we can have a switch statement which will call different functions based on the different commands that we receive. And our default case will just print out that we have an unknown command. Now let's create a function which will allow us to send data from one node to another. We want to connect to the internet, and we'll connect using the TCP protocol. So we'll pass in our protocol constant and then the address, which will be a string. This will give us back a net connection and potentially an error. If the error is not equal to nil, meaning the actual node is not connected, so we can't connect to the node, then we want to print out that the node is not available. And then we want to update the known nodes variable, which contains all of the different addresses of the peers that we can connect to. So we'll iterate through it, and then if the node is not equal to the address, we can append it and push it into this update nodes variable, and then we can replace the known nodes variable with the updated nodes. If, however, we do not get back an error, and we actually connect from one peer to the next, then we want to defer closing the connection, and then we want to use IOCopy to call the connection and then copy in the data that's being sent to the other peer. This send data function is going to be pretty important because we're going to be using it a lot, and you'll see how we're going to be using it in a moment. Let's start by making it so that we can send an address from one of our peers to the other. So we pass in the address as a string, then we create an address structure with our known nodes inside of it, and then we say nodes address list equals append nodes address list. And remember, this variable will contain the node address of the client that is connecting. So we're adding that to the known nodes for this client. Then we're making a payload by using our gob encode function, using the node structure, and then we need to create our request. So we'll use the command to bytes. We'll pass in the actual command, which will just be addr, and then we'll concatenate it with our payload as bytes, and then we can send the address and the request through the send data function. We have another function called sendBlock, which is very similar to this sendAddress function, except we're passing in a block from our blockchain as well as an address. We can use the block struct here to pass in the node address, which is this computer's address, and then the block as a bunch of bytes using this serialize function. We can then take all that data and use the gob encode function to take it and turn it into bytes, and then we can create a request by appending it to the command block, and then pass it through the send data function to send it to another node. I'm sure you guys can see the pattern that's sort of forming here. So now we need to be able to send an inventory. This will have an address and a kind, which will be strings, and then the items, which will be a two-dimensional slice of bytes. We'll create an inventory structure with the node address, the kind, and then the items inside of it. We'll create the payload by encoding that inventory structure into bytes. Then we'll concatenate it with a command, which will be IMV, and then we'll pass it through send data. For transactions, we'll take an address, which will be a string, and then a blockchain transaction. We'll put the transaction as bytes into our TX struct, along with the node address. We'll use gob encode to encode it into bytes. We'll create the request by adding the tx command to the front of the payload, and then we'll pass it through send data. We have another function called send version. This will take in the address string and then the blockchain. On the blockchain, it will call get best height, which is a function that we'll create in the next video. This function essentially will just go and check to see what the length of the blockchain currently is. Then we can use that best height to create a version along with the version and the node address. And then of course we can create the request and then call send data with the address and then the request. We do have two more primary send functions that we need to create. We have this send get blocks function, and all this is really doing is it's sending from one of our peers to another that we want to get the blocks from their blockchain. So we need a way of just saying, okay, well, we need to get some information from another peer. So we'll take and we'll make a get blocks structure with the node address inside of it. Then we'll make our request by appending get blocks to the payload, and then we'll call send data with the address that's being passed in here and the request. We'll do the same for getting data. This time, however, we also have a kind string and then an ID, which is a slice of bytes. And we'll use that to create a get data structure, which again we'll create a request with and then pass it through the send data function. So the send functions are the quote-unquote client side of things, meaning they're the messages that we're sending to peers, and then we need functions that will allow us to handle those messages. So we'll create these handle functions. So the handle address function will take in the command as a bunch of bytes, so we'll need a bytes buffer, and then we'll need to define the payload, which will be an address structure. We need to take the bytes and then serialize it into an address structure so that we can read it in our application. So we'll use the bytes buffer to get the actual command, and then we'll use gob new decoder and decode the payload into the actual address structure. Now we can go ahead and add the address to our known nodes variable, and we just want the address list, of course, so we'll just say append to the known nodes variable payload address list, and then we can print out that there are X amount of known nodes connected to our little network. So if we have 4 different peers connected to our network, this will print out that we have 4 peers connected to our network. Then we'll call another function called request blocks. And request blocks is a pretty simple function. It just iterates through our known nodes variable and then calls send get blocks on each of the nodes. It's essentially a way of making sure that all of our blockchains are synced with one another. Now let's handle receiving a block from another peer. Again, we create the bytes buffer and we create a block which will contain the data that we're decoding from bytes. We need to get the command out using the bytes buffer, and then we'll use the gob decoder to decode the actual buffer into our payload, which will be our block. Then we can take our payload block and put it into a block data variable, and then call blockchain deserialize on the block data to get back a deserialized block, and we can print out that we received a new block afterwards. And then we need to add the block to our blockchain, and we'll create a new function called add block, and we'll change our old function in our blockchain from add block into mine block, and we'll get to that in the next video. So this will then essentially just add the block to the blockchain, and then afterwards we'll print out that we've added the block to the blockchain, and we'll pass out the block's hash. Then we want to check to see how many blocks are in transit. If we have more blocks in transit, then we want to take the first block in transit and put it into the block hash, and then call get send data on payload address from, pass in the block command, and then pass in the block hash. So this will essentially go and get the next block if there is one. It will iterate through the blocks in transit variable that we have. So it will get rid of the 0th indexed and move down the index if there are more. Otherwise, we just want to create our UTXO set and then reindex the UTXO set so that we can properly read the blockchain. Now let's look at the handle get blocks function. This is very similar to the other functions that we've been looking at thus far. We got the buffer and then the struct that we want to serialize the command into, and we've got all of the decode logic. After we've decoded everything, we then want to call get blocks hashes, which will get all of the hashes from the blockchain. Again, this is another function that we'll create in the next tutorial. And then we can call send inventory with all of the blocks hashes inside of it, which will allow us to essentially hold an inventory of all of the different hashes. And then if one of the blockchains doesn't have the same hashes, we can say, okay, change the blockchain or re-download the blockchain. We then have a handle get data function. This will take in a request and then the blockchain again. And again, we have the logic to decode the actual request and then the payload into a get data structure. We have some if statements here. We want to check the payload type, and if the payload type is a block, then we want to get that block from our blockchain. So we'll call a function that we'll create in the next tutorial called getBlock, which will go into the blockchain and get the block based on the payload's ID, which will be in a slice of bytes. And then we'll pass that block to all of the other peers so that they can actually download it. If we have a transaction, however, then we want to take the payload ID, encode it into a string using our hex library, and then add it to the memory pool. And then we can call send transaction so that all of the other peers know that there's a transaction being passed around. Now let's look at how we can handle the version struct. So again, we get in all of those bytes with our request and we need to decode them into a version structure. We then want to get the best height from our blockchain, which is again using this function which we'll create in the next tutorial, which will allow us to receive the length of the blockchain. Then we want to get the other height, which will be the best height inside of our version structure. And we want to check to see if the best height of our local chain is less than the other height, meaning the other blockchain from the other peer has more blocks in it. And if it does, then we need to send a get blocks command to that peer so that we can actually sync up our blockchain. However, if our best height, meaning our local blockchain, has more of a length than the other height, then we want to call the send version function and pass in the peer that we want to send it to as well as our blockchain so that they can download our blockchain. We'll also run this if node is known check so that we can actually add to our known nodes. So we can add the address of the application that's checking to see if it needs to download the blockchain if it isn't already in the known nodes function. This node is known function is pretty basic. We just iterate through the known nodes variable. And then for each of the nodes, we're going to check to see if that node is equal to the address that's being passed into here. And if it is, then we'll return true. Otherwise, we'll return false. We need to be able to handle transactions because our wallet will be sending transactions to our miner and to our central node. So we'll take in all the bytes and then we'll decode them into a transaction structure. Then we want to take the transaction and put it into this txData variable. And then we'll call blockchain deserialized transaction with the transaction data inside of it, which will take the transaction and deserialize it into an actual transaction structure. Then we want to add the transaction to our memory pool with the key being the transaction's ID encoded into a string. And then we want to check to see if the node address is the centralized node, meaning the main node. Then we want to iterate through each of our known nodes. And if the node inside of known nodes is not equal to the node address, and the node is not equal to the payload address from, then we need to send the inventory with the transaction inside of it to the address. This will be for all of the other nodes that are not the central node and not a minor node. For all of the minor nodes, however, we want to check to see what the length of our memory pool is, and if we have more transactions than 2, and if the length of our miner address variable actually exists, meaning we do have a miner, then we want to call mine transaction on our chain. Mine transaction will go through the actual blockchain. It'll create a structure with our blockchain transactions. We'll then iterate through our memory pool, and we'll take each of our transactions from the memory pool and then verify those transactions and then append them to our transactions variable up here. If after we verify all those transactions, we get back a length of 0 for our transactions, then we know that all of our transactions are invalid. If, however, they do pass verification, we want to then create a Coinbase transaction with the miner address inside of it. Then we'll take the Coinbase and add it to our transactions. We'll create a new block by calling mine block on the transactions. And then we'll pass our chain into our UTXO set so that we can re-index it. Then we want to iterate through each of our transactions and delete them from our memory pool one at a time. And then we want to go through each of the known nodes and send that this new block was created. So this will then go ahead and update their blockchains to reflect the new mined block. Then if our memory pool is still greater than 0, we can call our mine transaction function recursively on our blockchain. If we get through this and we still have transactions in the memory pool, then we can mine the chain again. Finally, we need a function to handle inventories. So again, we have the logic to decode the bytes into an inventory structure. We can then print out what's inside of the inventory by printing out received inventory with D being the length of the payload items, and then S being the payload type. So if we have transactions, we can print out that we have 1 transaction or 2 transactions or whatever. And then if we have blocks, we can print out that we have 1 or 2 blocks. Then if the payload type is a block, then we want to add the payload items to our blocks in transit. Then take our payload items 0 index and get the block hash, and then call send get data to see if we can get that block from any other blockchain. And if this comes back and we do get the data, then we want to create a new in transit, which will be a 2-dimensional slice of bytes. And then we'll iterate through our blocks in transit, and we'll compare the block hash to see if they are the same. And if they aren't the same, then we'll add B to our new in transit, and then we'll replace our blocks in transit with the new in transit. So this will make it so that we can account for if we have multiple blocks. If the payload type is a transaction, then we want to get the first transaction ID, and we want to take that transaction and check to see if it's inside of our memory pool or not. And if it isn't, then we can call send get data, and then we can call it with the transaction and then the transaction ID inside of it. Now that we have all of these handle functions, we can come down to the handle connection function and add them to our switch statement. So if we get a case command of address, then we'll call handle address with our request. If we get the block case, then we can call handle block with the request in the chain. If we have the inventory, we can call handle inventory with the request in the chain. Get blocks, handle get blocks with request in chain. Get data will be handle get data. Transaction will be handle transaction. And then version will be handle version. We do want one more function, however, to actually wire all of this up. And that will be this StartServer function, which will run when we actually start the node. So we'll pass in the node ID and then the miner address string. And this string will be optional. So if the miner address doesn't exist, then it will just pass in an empty string. We'll then take the node ID and we'll concatenate it with localhost. So it'll be like localhost 3000 or localhost 4000 or whatever. And then the miner address will go into our miner address variable. To make it so that we're actually listening on the appropriate connection, we need to call NetListen with the protocol, which is TCP, and the node address. This will give us back a listener, which we want to then defer close on, and then potentially an error, which we want to handle. We then want to continue our blockchain, and we can do this by calling blockchain continue blockchain with the node ID inside of it, and the node ID will help us identify which blockchain belongs to which client. Then we can call defer blockchain database close, and then we can call go to spin up a go routine and call our close database function on our chain. This might be redundant, but I'm doing this just for the sake of safety. Next, we want to check to see if the node address is the centralized known address, meaning it's the localhost 3000. And if it isn't the localhost 3000, then we immediately want to call send version to the centralized address and then pass in our chain. So this will then immediately update the blockchain of any of our nodes that aren't our centralized node. Then we can create an infinite for loop, which will iterate through all of the messages that we get back from our listener. And for all of the messages that we get back from the listener, we can just call handle connection. And of course, handle connection should be on its own go routine as well, because we want it to be asynchronous. Alright guys, well that's it for today. I know I went through this code rather quickly, but that's because there's a lot of code and because there's a lot to explain. In the next tutorial, we'll be able to actually interface this network module with our blockchain. And as we're doing that, you'll see how it actually works a little bit better, because you'll actually get to see it in action as well. If you like this tutorial, feel free to subscribe and like. If you have any questions or comments, feel free to leave them in the box below. And if you dislike the video, then by all means downvote it as much as you like. Have a good night.